Chapter 6, Assembly Language Programming. What are the learning objectives? What are we going to learn in this chapter? By the end of this chapter, you should be able to show understanding of the relationship between assembly language and machine code. So, assembly language is a low-level language. The machine code is also a low-level language. Machine code is only binary, as you know, 0 and 1. That's all used for programming. Whereas assembly has a few codes, like they are called mnemonics, like add, sub, three like small short words which help you to remember and makes it easier to program, easier than what? From machine language. Then describe the different stages of the assembly process for a two-pass assembler. So the assembler, what is the assembler? Assembler is the program that translates assembly language into the machine code. Before translating it into machine code, you cannot run the assembly language. It's only the source code that you write in assembly language. You have to translate it into machine code. That is done by a program called assembler. The translator's name is assembler. Then trace a given simple assembly language program. Trace. You are aware of trace tables, dry running, that kind of thing on a simple assembly language program. So understanding that the set of instructions are grouped into instructions for data movement. So there is a set of keywords or language statements for data movement. Then there's another set for input and output of data. That is really only two, in and out. Right? Arithmetic operations. So for arithmetic operations, there is another set. Unconditional and conditional jumps. So those are the jumping into directing the execution into another place, depending on a condition or irrespective of any condition. Then comparisons, whether it's equal or greater, less, that kind of comparison. They show understanding of modes of addressing, show understanding of and perform binary shifts. So modes of addressing is something that is coming under assembly language coding. So that also we'll be learning. And also binary shifts. There's a thing called binary shifting. Logical shifts to the left and right. That is easy. That will come in the end of the chapter. So let's begin with machine code instructions. Machine code instructions are made up like this. There's an opcode, then the operand, a second operand or a third operand. An instruction can be either without a single operand, which means just this part. An instruction can be either only this part, just the opcode, without a single operand, without this, or with one operand, two or three, up to three operands, maximum three. Coding of the instructions can be different from one processor to another. So the processor, there are different types of processors. So to one processor, those instructions are okay, which is okay for this processor will not be okay for another processor. So they are called machine-oriented. Machine code instruction should be defined as follows. The total number of bits or bytes for the whole instruction. So this is the whole instruction. How many bits or bytes? The number of bits that define the opcode. How many bits for this? The number of operands that are defined in the remaining bits. Remaining, whether it's one, whether there is any operand, whether it's one or two or three. That information should be there, defined. And also, After that, whether the opcode occupies the most significant or the least significant bits. That means most significant is this side, least significant is that side. So where is this opcode, whether it's MSB side or LSB side? That also is important. Otherwise, it will be misread and there'll be errors. So opcode defines the action associated with the instruction. Then operand defines any data needed by the instruction. So if you say multiply by 2, then opcode is multiplication, operand is 2. Machine code instruction, a binary code with a defined number of bits that comprises an opcode and most often one operand. Most often just one operand. So let's take a simple instruction format. Where the opcode, now we saw opcode here, opcode and the operand. Now here we are dissecting or breaking them into some more parts like operation, address mode, and register addressing. Then the operand. So the opcode, what we learned earlier, now has 3 parts. One is the operation. There are 4 bits. So how many operations are possible? Then address mode, 2 bits. How many? Altogether. If you take these 2 altogether, how many? Let's take a look at some notes that I've made. Here, the opcode. Opcode is here. How many bits are there? 8 bits. If you take it apart like this, operation has 4 bits, address mode 2, and register addressing 2. So altogether, 8 bits. So the machine code instruction is like this, and a bit. How many? So to see how many operations, we have to know this. With 1 bit, how many values are possible? 0 or 1. So that means if you are using 1 bit to discuss the or define the opcode, then only 2. Only 2. Let's say this one. Operations are possible. If you use 2, then 0, 0, 0, 1, 1, 0, and 1, 1. Just like the binary counting. So that means there are 4 operations possible. We have 3 bits, 8 possible. So the formula is 2 to the power n. 2 to the power number of bits, 2 to the power n. So if it is 3 bits, then you have 2 to the power 3 is 8. If opcode is 4 bits, then 16 different operations. So here it is 4 bits, and we know that there can be 16 operations. How? Just like this, what I've shown here, starting from 0, 0, 0, 0, 4 bits, 1, then going on, 1, 1, 1, 0, then 1, 1, 1, 1. That's the end, the 15. This value is 15. So with this one, this is also value. Altogether, 16 values are possible. So if you put it into a table like this, the opcode, the operation, this is the whole thing. These 2 are the opcode, part of the opcode. And the first one is operation, 4 bits. So this is how 4 bits go on till from 0, 0, 0 to 1, 1, 1, 1. Altogether 16. No? 16 operations are possible. But if for each operation mode, there's an address mode also. And here you are using 2 bits. That means altogether 4. 4 are available. Right? Altogether 4 are available. Like this is 1. This is 1, 0. This is 1, 1. Okay, so 0. So altogether 4. Altogether 4 are available. 4 modes. 0, 0, 0, 1, 1, 0, and 1, 1. And now when you take, actually it should be 16 into 4, no? Because for each of these, there are 4 modes. Then for 16, there should be 64 modes. And how is it made up? Like this? You start with this 4 bits as 0. See, while this is 0 and this is also 0. So that is one value. And then it goes up to like 0, 0, 0, 0, 0, 0, 0, 0, 1. While this is 0, 0, 0, this one is 0, 0, 0 here, up to 1, 1. That means 4, like this. 0, 1, 1, 0, 1, 1. So four modes here. While this is 0, 4 modes. Then while this is 0, 0, 0, 1, another 4. Likewise, it goes up to this 16 times, which gives you 64 modes. Right. Then how many operations are possible with each address mode? With each address mode, only 4. Like that, because there are 2 bits. Then here is another, again, the same thing I put there in a different way, but slightly different. But you can go through that and see how it is changing. Starting from this, here I am changing this one, while this is 0. So anyway, you can take. Whichever way you take, it's the same. Earlier I took, while this is 0, this is changing 4 times. Now, while this is 0, this is changing. So likewise, it goes finally total of 64. Then transfer of bits 16 to 23 is shown by the register notation. There is a thing called register transfer notation. Something like this, you have to, like pseudocode, you have to show that. So transfer of bits 16 to 23. Now I have numbered these bits from 0 from this side. 0 to 15, which is 16 bits for the operand. Then the next one is 16. 16 to 17, register addressing mode 2 bits. 16 to 17, 16 is 1, 17 is another, so 2 bits. Then here address mode 2 bits, 18, 19. And here 4 bits, 20, 21, 22, 23. So if you want to transfer this opcode 16 to 23, this way, 16 to 23. Transfer of bits 16 to 23 is shown by the register transfer notation, that is in the check execute cycle, CU. Now, do you remember CU? What do you remember? CU. Right? Control unit. Yeah. That's simple. Control unit. So into the control unit, the data must go, all the instruction, which is from this to that. Then only the operand will come next. So this is the way, not 16:23, but 23:16, because we are measuring from here. We are reading from here, 23 to 16th one. This is the way. So the assembly language itself, now after learning about that, the assembly language. With machine code, we can directly control actions taken by the CPU, but it is very difficult to write long programs in machine code without making a lot of errors. So the answer is assembly language. Can you write instructions in like this 0, 0, 0, 0? Very difficult. Very difficult. So because of that, the answer to that is the assembly language, which has few words also. Then the assembly language, again, the term is defined here. A low-level language related to machine code where opcodes are written as mnemonics. And there is a character representation for an operand. So mnemonics, the M is silent, so you pronounce it as mnemonics. That means short words, like names, short words. So that is very easy, easier than the machine language. But what is assembler? A program used to translate an assembly language program into machine code. For each machine code instruction, there is an equivalent assembly language instruction which comprises a mnemonic. Okay, now you know what it is, a symbolic abbreviation for the opcode, a character representation for the operand. For the operand, the second part, a character representation. Translator is the assembler. Translator in this case is called the assembler. Using assembly language is easier than machine language. The following special features are allowed in assembly. Comments. There are 5 things which are allowed. Comments, as you know, in Boolean, Python, we have done. Like this, in Python, you have comments, you know about comments, and then this is the way in pseudocode. This is just going out little bit out of the section, the topic, just to remind you about these two. It's very important. Pseudocode comments are like this. Yeah, so let's get back to the assembly language here. And what are allowed, what are allowed in assembly? Comments. So comments are allowed, which are very useful in any language. It's not for the program, remember. Comments are not for the program, but for the humans, the programmer and those who maintain it. Then the second one is symbolic names for constants. When there are constants, right, values, there you can give a symbolic name, right, a label. Like. Then the labels for addresses. Certain addresses, you can give labels. You might recall, you might want remember in Excel or Lotus, those days it was Lotus and Excel, now it is called Excel, Microsoft Excel, spreadsheets or similar packages. You have the address, A5, K7, like that you have names for addresses. But those are like column, row and column. But you can give a label for an address, like in spreadsheets, you remember naming a cell or naming a range, so that when you it won't be relative, it's specific. Specifically, it's label the addresses. For label for addresses also allowed. Then another thing called macros. That is a sequence of instructions that is to be used more than once in a program. So if you are using more than once, like repeating set, you can put it aside and give a label and call it a routine, subroutine, a procedure, or a function. You are familiar with those things. Then one more thing, directives, an instruction to the assembly program. So this is not an instruction to the computer, to the machine, but it's to the, and not to the programmer either. This is an instruction to the assembler program. An instruction to the assembler program. So we are giving an instruction to the assembly program for when translating to follow this instruction or the directive when translating the source code. So again, the term is defined, directive, and instruction to the assembler program. Remember, assembler program. Not to the machine code, or not to the assembled program, or not to the programmer. It's for the assembler. Here's an addressing mode, the symbolic, relative, and absolute addressing. 3 modes of addressing. In means a single number is input at the keyboard and its ASCII code is stored in the accumulator. Accumulator is called ACC, you will know later, accumulator. So if you revise a little bit, you go back to chapter 5 and see the processor fundamentals, you will remember that accumulate the registers. Accumulator is a general purpose register. Then there are other registers. Remember, PC, MAR, MDR, CIR, all those things. Okay. A single number is input at the keyboard and its ASCII code is stored in the accumulator. So accumulator is a register, general purpose register. And the name is not given here, it's understood, it's accumulator. Next one is sub 48 with a hash mark in front. That means subtract. This subtraction converts the ASCII code into the binary code for the number that is in the task 6.01 also. You have it. Sub number 48. The ASCII code subtraction converts the ASCII code into the binary code. Earlier it was the binary. It was the ASCII code here when you input. But this will take off this for number and make it absolute number, normal number. When we do a sample, you will understand. In a little while, I'll do that. Then the next one is store max. Max is a label. The number in the accumulator is stored at the address labeled max. Like in our terms, a variable, an identifier, max, to store some value in max. The number in the accumulator. So always the accumulator is not mentioned here either, but it's understood that from the accumulator, what is there, the value that is there in the accumulator now gets stored in max. Next one is LDM hash 0, which means load immediately, now 0. Load 0 into the accumulator, where accumulator. Then store total. The 0 in the accumulator is stored at the address label total. So we have two labels now, max and total. Store count, a third label. The 0 in the accumulator is stored at the address labeled count. Then here's label start LP, a single number in. The instruction is in. This is like a location, start LP, in. A single number is input at the keyboard and its ASCII code is stored in the accumulator. Same as this. But here is another place where this is executed. Then sub 48, same thing here. The subtraction converts ASCII code into the binary code of the number. If you compare this, it's the same. Then add total. This is new. Adds the value at address label total. What is there in total? To the value in the accumulator. What is there in the accumulator? Again, I am repeating to remind you that there is no mention of accumulator, ACC here. But it's understood. Add the value of what is there in total to the accumulator. Adds the value of address label total to the value in the accumulator and stores the sum in the accumulator. Still in the accumulator. Not moving anywhere. After adding, it is stored in the accumulator. Store total. Now, you already know the meaning. The number in the accumulator is stored at the address labeled total. LDD count. Load direct. You will learn these in detail later. These are the mnemonics. Instructions. Loads the value stored as address count into the accumulator. So what is there in count will be loaded into accumulator. Increment. Increase by 1 or increment ACC. That's the accumulator. Adds 1 to the value in the accumulator. Whatever that is, the value there is in the accumulator, add 1. That's incrementing. Then compare max, CMP. Compares the value in the accumulator with the value stored at address max. So, if you have, it's a number, the hash sign comes. If there is no hash, that means it's an address. So what is there in max? Whatever there is in max, compare with the number in accumulator. And if it is true, there is no instruction here. If it is not true, here there's an instruction. JPN, jump. Jump means, okay, bypass this and go to a particular place. The start LP. The place is start LP. So you have to go back here. Resume from here. It's like a loop. So remember as not jump, and if it is not after the compare, this comparison, if it is not equal, JPN. If it is equal, they will say JPE. Later on, you will find it. JPE. If it is equal, then do that. If it is not, do this. So we are not going to end. We are going to this place in and then continue. Until now this max is also, max has a number and these are changing a count and ACC and all that. They are changing values. When at a certain point, when you compare max, if it is equal, then this will not be done because this has to be done only if it is not equal. But since it is equal, this will end here. It comes to the end. So just the explanations are compares the value in the accumulator with the value stored at address max. We did that. Then this one, what's the meaning? If the compared values are not equal, the program jumps to the instruction label start LP. That's why we started here again. Then these are the labels. A labeled address where a value can be stored. Right. So an assembly program using symbolic addressing with explanations. A label is written with the following colon, which is ignored when the label is referenced. So label is written with a colon here, but when you reference it, no colon. So here is a sample in. So let's say we'll take from here. The first instruction is in. So for that, in the character, let's say we input 5. Correct input is 5. Then the denary equivalent of 5 in the ASCII code, how much? 48 is 0. Right? So 49 is 1, 50, like that. If you add 5, denary is 53, and the binary code is this. So to the accumulator, this will go with this instruction. Then the next instruction is sub. Yeah, sub 48. Sub 48 number. So what does that mean? The denary is 48. Then the binary code is this 32 and 16, 48. When you subtract, deduct, you get this. And what does this mean? This is 5. So here, though we entered 5, the ASCII code goes. So we have to convert it into normal numbers, values. So this is made 5 here. Then store max. Store max means store it in the label or the variable or the memory location called max. So it's here. Then LDM 0. LDM 0 means load immediately the number in hash 0. So 0 is loaded here. And store total. So total will get this. And it goes on. Goes on until a certain condition is met and finishes, end. The use of symbolic addressing allows a programmer to write some assembly language code without having to bother about where the code will be stored in memory when the program is run. So we have to do a little bit more in assembly than high level languages. Well, in high level languages, we never thought of, and we don't think of line numbers or in the memory addresses. But here, we have to check that out, where the code will be stored in memory when the program is run. So the symbolic one makes it easy, symbolic addressing. However, it is possible to write assembly language code where the symbolic addressing is replaced by either relative addressing or absolute addressing. So here is relative addressing and this is absolute addressing. So we are going to compare these two. First instruction in both instructions are same. The opcodes are the same. Operand also same, 48. But here, what does this mean? BR. So there is a place to start, no? There is some place to start in the memory. If we start from 0, then this means plus 15. Store, we don't tell the name. Here address, directly you say, if you are starting from 200. Now that also we specify. There is no case of changing here. Absolute means that. Absolute is load this program and the first instruction to be in 200. And when you say store 215, so 215 is here. It will be the max or whatever. The first one is, yeah, whatever which was there in, let's see, store max, yeah. So store max 215. So this will be max, but no labels, right? These are absolute addressing. So 216, 217. What happens here is the base, BR is base register. There's a base. If it is 0, then BR, that is 0 plus 15. So that will be here. Max. Then 16, the next one, total or count or whatever is like 15, 16, 17. Same way here, 15, 16, 17. So this is, if it is loaded in at 0. Supposing this got loaded into 500. First instruction at 500. Then what will this do? Store 500 plus 15. This 15 will not change. That's the offset from here to how many cells away. But this will change. This will be 500 if you start at 500. So that's not very difficult. Then the relative addressing. A special function base register, that is relative addressing, is this. This is a description, explanation. A special function base register contains the base address. The contents of this register can be used as indicated by BR. No labels for the code. No labels. We don't give any names here. Offset from base address, which is the address of the first instruction in the program. So this is the base address B0. If this is 600, then this will be 600 plus 15. Absolute addressing is different. Again, no labels for the code, but this time identifying actual memory addresses. As I told you earlier, actual memory addresses. It won't change. This 205 means 205. It won't change. But here, when you say 5, it might end up as 605. Because if this is 600, that plus this. The first instruction in this, but yeah, no labels for the code. But this time, identifying actual memory addresses. Actual memory addresses, these. Which is, sorry, the first instruction in this example program is to be stored at memory address 200. So that's absolute. We don't know, we know the place. In this case, relative addressing, we don't know. It will be decided by the OS at that time. Then we come to the assembly process for a 2-pass assembler. Let's go through the notes to see whether there is anything useful for us. Yeah, comments, as I explained here in Python and in pseudocode. So if you say LDM 0, load 0 into the accumulator. So total, the 0 in the accumulator is stored at the later. So you can go through this anytime. This is available on the website, web page. You can go through this at any time you want. It will be useful. If you have any doubts or clarifications in the text, in the tutorial, you can go through that. Assembly process for a 2-pass assembly. A number of things that have to be done with the assembly language code before any translation can be done. So like preliminary things, we have to like preparation in the first part. What are they? Removal of comments. So I hope you remember. If not, go back and see the 5 things that are allowed. First one is comments. Removal of comments, then replacement of a macro name used in an instruction by the list of instructions that constitute the macro definition. It may not be clear to you. When I go to the notes and show you an explanation, you will understand that. Removal and storage of directives to be acted upon later. So understand that, try to remember this. Directives, you remember directives, they are not to the program, they are not to the machine, they are not to the programmer, they are to the assembler, the translator. So remove those things because they are not relevant. But if they are to be acted upon, then we have to store it. Store safely somewhere these directives in another location so that the assembler can refer to it when necessary to act upon those directives. So in Python, this is a sample of comments, program name, who is the author, what's the purpose, the date, various things, modified date, what's the purpose, and all those things. So sample program, this one. So these things will be removed. Not in Python. I'm just taking Python because you all are familiar with Python, not assembly. So in Python, if you understand, then you can visualize it, what is happening in the assembly. So that is that. Comments will be removed. Then the other one is what? There are 3 things which have to be done. Removal of comments. Then the other one is replacement of a macro name used in an instruction by the list of instructions that constitute the macro definition. So think of this. In the main program, you have a thing called print name. So in high-level language, we don't call these macros. We call it a procedure or a function. So print name is not there. I'll highlight the main program. That's all in a Python program. Remember, again, I'm repeating because otherwise you might confuse this with assembly. So here is the main program where this is not defined. It's defined outside here, print name. But the instructions are name equals input name and print hello name. So this will stop. This again, this will be helpful to you. Remember, when this is encountered, we'll do this, not print done. Print done. This will be after this is finished. When you finish this, that is input a name and say print that particular name. Then you come back here to the next instruction. Then only it will say print done. So this is replaced. There is only one word here, no? That is replaced by the exact lines, something like this. So the main program will look like this before the thing is translated. Now you understand what is meant by replacement of a macro name. The name is replaced. This print name is not there now, the new one. Intermediate program, print name is not there. It's replaced by the real instructions. And then finally, removal and storage of directives to be acted upon later. So those you have to remove from the main program, but store them for later use. A 2-pass assembler is needed so that in the first pass, the location of the addresses for forward references can be identified. So whether it's plus 15, 16, 17, those things have to be identified first. And then to achieve this, during the first pass, the assembler uses a symbol table, a thing called symbol table. And what are the contents? The symbol and the offset, like here, max. Yeah, it's 15, the offset. So 0 plus 15. So max is at plus 15, total is 16, count is 17, and start LP at 7. Let's see whether this is correct. 15, 16, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 15, 16, 17, and then start LP at 7. 15, 16, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 17, 15, 16, 17. Now here it doesn't show start LP label. Start LP. Start LP means go back here. Go back here. So that label, we saw it this, where is start LP? 7 here. 7. So you go back to 7 and start here. Sub 48. Okay. Start LP in and then sub 48. Start from there. So this is the symbol table, remember. A completed symbol table for the assembly language program in table 6.01. In this example, the first entry made in the offset column is the +7 for start LP. LP is loop, right? Start loop. Sorry, a label. For the second pass, the assembler uses the symbol table and a lookup table that contains the binary code for each opcode. Remember the opcode? So opcodes are these, we saw always, and the operand on the right side. Left is the opcode, then the next one is operand. So in is assume that it's 0001 and 0000. That is the binary code for the opcode in. And then for the opcode sub, it's this. Likewise, for all the mnemonics we had, there is a translated value here. It's a table. If no errors have been identified, the output from the second pass will be a machine code program. Just like high-level compiler also does the same thing. If there are errors, it will stop and then give a list of errors. Here also, if there are no errors, then it will compile fully and then produce the object code, the executable file. So this shows machine code created from assembly code. So we have the assembly code here, and we translate this, like for sub, if you put the respective number, it will be like this. For in this, so the program will look like this. Opcode is this. Let's take, for example, in. For the in, this is the assembly code. On this side, the assembly code is there, and this is the translated machine code. So in is 0001. Let's see, 4 zeros. In is 0001 and 4 zeros. Sub is 0110 001. 0110 001. That's a sub, right? Sub is this, and the full instruction is sub 48. Number 48. So sub code is this opcode. Then the operand is 48. So 48 here, and operand, we saw that there were 2 bytes. Yeah, two bytes. So the operand will be like this: 1, 2, 4, 8, 16, 32. So 32 and 16 is 48. 32 plus 16 is 48. All right. So opcode sub, this is sub, this is 48. Operand 48. So sub 48 is written like this. Likewise, it goes on. So finally, this is the machine code, ended up executable file, machine code. Most of the instructions have an operand which is a 16-bit binary number. So that's why the operand, we have 16 bits, 4 nibbles or 2 bytes. Usually this represents an address, but for the sub and LDM instruction, the operand is used as a value that you already saw that, no? There is no operand for the in and end instruction. That also I suppose you saw is in. In the mnemonic section, it's just in. And there is no operand for that, just in. Right? And end also same, end. Just the opcode, no operand. There is no operand for the in and end instruction. The increment, INC instruction is a special case. There is an operand in the assembly language code, but this just identifies a register. In the machine code, the register is identified within the opcode, so no operand is needed. So that's why it's just incrementing or increasing by 1. The machine code has been coded with the first instruction occupying address 0. This code is not executable in this form, but it is valid output from the assembler. So this, if you just type like this and then put, it will not execute. But for learning purposes, that is enough. Because it looks like machine code. And we are not going to try to run it. Changes will be needed for the addresses when the program is loaded into memory, ready for it to be executed. So when you load it afterwards, since it is relative, it's if it is relative, then you have to some addresses have to be adjusted and calculated. 3 memory locations following the program code have been allocated a value 0 to ensure that they are available for use by the program when it is executed. That is a max, total, and count. It's interesting. Some values, some operations are there. Let's check this out. Addressing modes. So we are done with opcodes, operations, and all that. Now here is the addressing mode. So this again, I have brought this up here for you to revise. This is the instruction structure. Addressing mode is when the instruction uses a value. This defines how the operand must be used to find the value. What is that? The addressing mode. So here it should give a way to find the location, find the value. Must be used to find the value. So addressing mode 2 bits, 4 different modes. And what are they? Immediate, direct, indirect, and indexed. So earlier we saw that if there are 2 bits, we can have 4 modes. Right? So addressing mode here we can have 4 modes. So immediate, the operand is the value to be used in the instruction. And you have a hash sign in front. Is an example. Sub and the addressing mode is this. And for direct, the operand is the address which holds the value to be used in the instruction. That is add, if you say add total, it's directly where the total, the address total, you will find the contents. Access total and then get the content. Indirect is a little slightly different to this. The operand is an address that holds the address which has the value to be used in the instruction. Like if you say, I poured the drink to a glass where there was a glass inside. There was another glass. So you take the inside glass and pour the drink. That's like that. Here, the address given here is another address. The value given in this is another address. You have to access that address, then only you will get the contents. Whereas here direct means directly you have that address, that's all. And that address you will have the value. I'll repeat this. Indirect, you address the indirect operand will have, it's a LDI. It's normally indirect is LDI. LDI 200. That means you check the 200 address. In that 200 address, another address is given. Not a data value. Another address is given. You take that second address and get the value stored there. That is indirect LDI. Indexed. The operand is an address to which must be added the value currently in the index register. So that is like a LDX. Not I is for indirect and X is for index. But there, if it is 200, the address given is 200. And the index register, you have to look at the current value in the index register. If it has 3, then that will be 203. I'll read this again, it will be clear. The operand is an address to which must be added the value currently in the index register to get the address which holds the value to be used in the instruction. So you have to make up the address to be accessed. If it gives 200, look at the index. Then if it is 3, you add 3 to 200 and 203. Now get the contents of address 203. For immediate addressing, there are 3 options for defining the value. So immediate means this one LDM. This when you give these numbers, it's always numbers, because immediate you won't get an address. Immediate means that load 48, something like that. No address. So for that, hash 48 specifies the denary value 48. If you want, if your number in question, what you are dealing is 48, if it is denary, then you just put hash and 48. And this one, if it is a binary number that you are dealing with, then you have to specify like this, hash B, binary. Or else, if it is hexadecimal, hash and ampersand. Ampersand is this and sign. So those 3 also you must remember. Have a good look. Denary, no prefix, only the hash mark. If it is binary, the prefix is B here with the hash mark, and hexadecimal, hash ampersand. Assembly language instructions. Data movement. So as we saw at the beginning, these are the things that we'll be dealing with now. First, data movement. These types of instruction can involve loading data into a register or storing data in memory, either to a register or from a register to the memory. This table contains a few examples of the format of the instructions with explanations. LDM hash N means immediate addressing. So this M, easy to remember, LDM is immediate addressing. Load the number N, is whatever the number here, into ACC. LDR hash N. Immediate addressing, load the number N to IX means index. Right? IX is index register. So generally these things are to accumulator, but if it's a LDR, then to IX. If it's LDD and an address here, not a number like this, LDD address, direct addressing, load the contents of the given address to ACC. LDI, indirect addressing, the address to be used is at the given address. So one address gives another address where the contents are. Load the contents of this second address to ACC. LDX address. Indexed addressing. Form the address from the address given here plus the contents of the index register. Copy the contents of this calculated address to SEC. Then move to a register, not an address. Yeah? Not an address, not a number, register. Move the contents of the accumulator to the given register. Right? Index register. Then store and given address. Store the contents of ACC at the given address. So, assembly language instructions, data movement, we did this part. And then we come to a very small program, simple program. This diagram shows data stored in memory. This is the memory address, 100, 101. Then the contents, memory contents are these. And there's the accumulator here, and then the index register. And this is index value. Index value is this. What are the instructions? LDD 103. LDD 103. What happens? Now it's difficult to remember, but once you do these 2-3 times, it will be easy. So you read this and see. When you are doing alone, if you can't remember. So LDD 103 means the value 110 is loaded into the accumulator. Right? This 103 is an address. So 103 address has the contents 110. 110 is loaded into the accumulator. Next one is LDI 106. LDI means indirect. So 106, you just check 106 and see what is there, 101. And then you check, as I told you, LD indirect is another address, second address. So 101, go there and then see the contents, take it, put it here, 208. The value 208 from address 101, not the given 106, is loaded into the accumulator. Next is store 106. So what is, when you store, it will be from the accumulator to the location. So what is there in the accumulator now? After our previous operation, 208. 208 is stored, loaded into accumulator. Now when you say store 106, value 208 will go into this. This 101 will be overwritten by 208. The value 208 is stored in address 106. So this 101 will be erased. 208 will be written there or stored. And move IX. The value 3. Index value is 3. Value 3 from the accumulator is loaded into the index register. Sorry, I skipped this. I slipped. Next should be LDD index value. The value 3. So this 3 is loaded into accumulator. Loaded into the accumulator. After that, move IX. Just like store. Like store, but the place is here index register. So here we have 3 because we moved it there. Now we store 3 in this index register. The value 3 from the accumulator is loaded into the index register. And LDX 102. 102. And now this X, remember, LDX is indexed addressing. So index mode 102. We have to check 102 and get the address from there. It says 201. So where is 201? Sorry, I'm sorry. That's a mistake. LDX is 102 plus this index value. If you go through those explanations on the address modes, you will find operation code. The index value 3 is added to this. The value 206 from address 105. Right? 102 plus 3 is 105. Go to 105 and you will find 206. The value 206 from address 105 is loaded into the accumulator. So that's a simple operation, and any operation is done the same way, on the same principles. So if you get this right, that's very important to get this right. If you don't, then you better repeat this lesson up to this point and then try to figure it out. And then all the other programs will be similar. So any exam question also will be easy. Input and output, there are two instructions provided for input or output. In each case, the instruction has only an opcode. There is no operand. We saw it earlier. The instruction with opcode in is used to store in the ACC, that is accumulator, the ASCII value of a character typed at the keyboard. So in is, always remember two things. What is typed into the keyboard, and then the ASCII value of that is stored. You remember, you will recall, if you wonder whether you remember, when we were doing ASCII in chapter 1, we found that when you press a key, there is a chip inside the keyboard, and it has the ASCII code. It will translate it into the ASCII code, relevant respective ASCII code, and then send to the CPU. So here it will be easy, no? The instruction with opcode in is used to store in the ACC the ASCII value of a character typed at the keyboard. So no additional conversions. From the keyboard, it comes ASCII. The instruction with opcode out is used to display on the screen the character for which the ASCII code is stored in the ACC. So one character at a time it will come. What is there in the ASCII? What is there in the ACC? This ASCII code. It will be translated and then displayed on the screen. Then comparisons and jumps. A program might need an unconditional jump or might need a jump if a condition is met. In the second case, a compare instruction is executed first. So unconditional, no compare steps. But if it is a conditional jump, then a compare has to be done, whether the condition is met or not, or satisfied or not. So this table shows the format for these types of instruction. So jump, JMP, jump to the given address. CMP, address, compare the contents of ACC with the contents of address. Compare, CMP, another general compare with number. Either this one is with the address, compare with the contents of the address. Here, compare directly the number given. Compare the contents of ACC with the number n. CMI, that's also a compare. CM is compare. Indirect addressing. The address to be used is at the given address. Compare the contents of ACC with the contents of this second address. Not the address given here, but the address, this address will give another address and take the contents of that to compare with what is in the accumulator. The JPE is following a compare instruction, jump to address if the compare was true. Take the last letter of true as E here, or you can take it as equal. If it is equal, then this, or true, TRUE, true. And JPN is following a compare instruction, jump to address if the compare was false. So you can, easy to remember if you take it as N, not equal. If the compare is not satisfied, then jump to whatever the address given here, this address. Otherwise, jump to this address. Then the arithmetic operations, as you know, they add, sub, band, int, these things. Add addresses, add contents of the given address to the ACC. Add number, add the denary number to the ACC. Sub address, subtract what is given in the address. Sub this number, given number. Increment or increase by 1, the register, the relevant register, add 1. Decrease or decrement is reduced by 1, the particular register, ACC or IX, either accumulator or index. Then figure 6.03 shows a program to find out how many times 5 divides into 7. The following should be noted concerning the program. The first three instructions initialize the count and the sum. This is that what we did earlier. The operation is described here with lines and arrows. So this is also very useful. If you can, when you're free, you can go through this. It's available on the website. No. So the first, these are given. The first three instructions initialize the count and the sum. So that means this count and the sum. So 100 LDD 200. Okay, then there's another one. The instruction in address 103 is the one that is returned in each iteration of the loop. So we have to make note of it as 103. The start of loop is this 103, LDD 202. In the first iteration, it is loading the value 0 into the accumulator when this value is already stored, but this cannot be avoided. With experience, you will know that when you are doing a program and we have a algorithm like this, and we have a loop, sometimes one or two are repeated because you can't help it. If you don't do that, this will give a wrong value. So it doesn't matter the redundancy, one or two instructions. In this case, it's one. Then the next three instructions are increasing the count by 1 and storing the new value. So this LDD, first of all, this LDD 200. So 200 will be loaded into 200 is what? You must not get mixed up. LDD 200 means 200 is an address, not a number. If it's a number, the hash mark should be there. So at 200, you have 0. So this means load 0 to accumulator. Next one is store 202. So what is there in the accumulator? 0 to store in 202. So this will become 0, 202. Then store 203. This also will become 0, 203 also 0. Afterwards, LDD 202. So again, an address, not a value. So go to the address 202. This whatever that is there, we did earlier. Okay. Store 202, that was 0. So the 0 will be loaded. Then increase ACC. So ACC, what is there in ACC? Now if it is 0, then ACC will become 1. Then store 202 again. 202 will become 1 here. Then LDD 203. What is in 203 will be loaded into accumulator. Then add 201. 201 is 5, so we add 5. 201, yeah. Store 203. So put that number in 203 here. And add 2, compare 204. Now is the first comparison. Compare with 75, whether this, what is in accumulator? Is it 75? Okay. Follow carefully. Compare 204. 204 is 75. And if it is not equal, it's not equal because here is 0. Then if it is not equal, jump to 103. Jump to 103. So 103 here says LDD 202. So in 202, whatever the value here will be loaded to accumulator and then continue. At this point only, an increment and store and this continue. Finally, until this becomes 75. Until accumulator has 75 to compare with 204. When compare with 204, if it is not equal, you jump to 103. But if it is equal, what happens? this doesn't happen, this will happen. LDD 202, out means output, what is the final number, then end. 202 will, I'll give a clue, 202 will have 15. Well, the question is to divide 75, find out how many times 5 divides into 75. It's 15 times. So the answer will be 202 will be 15. Load 202 and then load LD directly 202 and out. That means display the answer. So the next three instructions are increasing the count by 1 and storing the new value. Instructions 106 to 108, add 5 to the sum. Instructions 109 to 110, check to see if the sum has reached 75. And if it has not, the program begins the next iteration. Instructions 111 to 113 are only used when the sum has reached 75, which causes the value 15 stored on the count to be output. So the number here 203, 15 will be output. So I have given this program how this is a trace table, rather. A trace table on how to check it out. Whether, though we did this mentally, we can trace this like this. See whether it's really happening. I put 1, 0, and 75, the initial values. And take it from, SEC, load 0, then you put SEC 0. These are the values that are stored here. 200 is 0, 201 is 5, 202 is, that is later. This became later. Initially, 204 is 75. This one. So the sum 203 will increase every time, every loop. It was 0, it will become 5, then it will become 10, 15. And finally, I have given some blanks here. That means it will go on for a long time and it will end up when it is 75. So you compare, because 75 is here, it doesn't, since it is not changing, it's not written down below that. It's only there. So it has not changed, it's still 75. When you compare these two, if it is equal only, it will stop and then output the final one is the output. 15 times. That's the answer. And these are the three that we use: JMP, JPE, and JPN, the jump statements. Here's another one, a task you have to do. This will help you to look at this, how it is done. Then we come to the shifts. Shift operations. LSL is logical shift left, where the bits in the accumulator are shifted logically n places, the number n here, to the left, and LSR to the right. Logical shift is where bits in the accumulator are shifted to the right or to the left, and a 0 moves into the bit position located. Supposing this, this has to shift 3 places. 3 places. Left, LSL. What happens? This one will move out. It won't come in. It just moves out. We lose it. And 0 will come here. This one will come. Likewise, all will come this side. And there's a empty space here, vacuum. Null value here. For that, you have to insert a 0. Okay, not 1, always 0. So if there are 3 places, then you have to insert 3 times. Right? There is only 1. Only 1 shift. And here the result is This one has become 0. This has come, this has come here. Each one has shifted one place and a 0 has entered from this side. So what is the implication of that? Because the shift operation moves a bit from the accumulator into the carry bit in the status register, this can be used to examine individual bits. Carry bit means like, the sum and carry. When you add 1 plus 1 in binary, it's 1, 0. And the 0 is the sum and 1 is the carry. So because the shift operation moves a bit from the accumulator into the carry bit in the status register, this can be used to examine individual bits. So in the status register, remember that when we were talking about registers, there was a register called SR, the status register, which can have 8 different values. So here, one of them is the carry bit. A logical shift cannot be used for multiplication or division by 2 when a signed integer is stored. Before that, I'll explain the multiplication and division. Take this 0, 1, all these zeros give you 64. Then if you shift to the right, this is what happens. 1 0 will be lost from this side and another 0 will enter there. The value of this is 32. And similarly, the third one, this is 16, this is 8, and this is 4. So if you take a pattern like this, and if you check what has happened, this has halved, or division by 2. 64, half of 64 is 32, half of 32 is 16, 8, 4. So that's division. To the right and left is multiplication. Left is like if you start from here, what happens? This one is shifting one place, another. So that will become 64, like this, 8, 16, 32, 64. So the left shift is multiplication by 2. LSL cannot be carried out on a signed integer. Why? Because the sign is, the MSB bit is the signed bit, for a signed integer. So you will lose the sign. Negative ones become a positive, positives become negative. So it's disaster. You can't do that. Because the shift operation moves a bit from the accumulator into the carry bit in the status register, this can be used to examine individual bits. A logical shift cannot be used for multiplication or division by 2 when a signed integer is stored. Just now we saw that because we will lose the sign and the value will be entirely different. This is because the operation may produce a result where the sign of the number has changed. Cyclic shift capability. Here a bit moves off one end into the carry bit, then one step later moves in at the other end, like a cyclic. All bit values in the original code are retained. Left and right arithmetic shifts are also likely to be available. These work in a similar way to logical shifts, but are provided to the multiplication or division of a signed integer by 2. The sign bit is always retained following the shift. So cyclic shift is leaving from this side and entering from there. Nothing is lost. All the bits, but may be jumbled. That is also there. Then the cyclic shift definition. Similar to a logical shift, but bits shifted from one end reappear at the other end. Arithmetic shift uses the shift to carry out multiplication or division of a signed integer stored in the accumulator. Bitwise logic operation. Bitwise logic operation and there are two, XOR 2 and OR 2. It's a number here, address, number address for each. Bitwise AND operation of the contents of ACC with the binary number n. I'll explain to you what it is. This is AND, of course, contents of the address. Likewise, goes on here. So bitwise operations. Let's take this and if you have and number a number like and hash B is for binary, bitwise AND operation of the contents of ACC with the binary number n. Each, now there will be a binary number here, each bit to be ANDed, bitwise AND operation of the contents of ACC. Whatever that is there in the ACC, you AND it, whatever, bit by bit. Let's take like this. So if the ACC had this number, and hash bn, the operand is this. Take these numbers here, this one there, and this one below that. And what you do is you 0 and 1. Think of the truth tables. Think of the truth tables you've done. 0 and 1 is 0. 1 and 1 is 1. 0 and 0 is 0. 1 and 0 is 0. 0 and 1 is 0. 1 and 1 is 1. Only 1 and 1 is 1. The others are zeros. Okay? If it is XOR, remember the XOR, that's different to the others, the truth table. Only if it is unequal, it will be 1. And if it is equal, the inputs are equal, then it will be 0. So here, 0 XOR 1, which is this, results in 1. And 1 or 1 XOR 1, because they are equal, it's 0. 0 XOR 0 equals 0. Only when they are not equal, then you get 1. So this is the answer to that one. And or 1 or 0 is 1. 1 or 1 is 1. 0 or 0 is 0. Likewise. Okay? Here is a table for you to remember, because you get, if you want to reset means make all the bits zeros. So if you have a number like this, and if you want to, the questions will ask, the examiner will ask you, how do we make all these zeros, or how do we reset this number? And hash 0. Binary number, all zeros, what happens? Because it's AND, if there is a 0 here, whatever the number which is there will become zeros. Likewise, if you want to have the same number, do an operation, but retain the same numbers, then also AND, but 1. What happens? 0 and 1 is 0. 1 and 1 is 1. So whatever the number which is there will be retained if you do this. And 0 will reset and 1 will set. So if you want to keep the same as another way, or all zeros, that also will keep the same. And invert, if you want to invert a certain value, 1 to become 0, 0 to become 1, then of course XOR 1, all ones, XOR 1. If you want to keep the same, so to keep the same, there are 3 methods. With AND also you can, with OR also you can, and XOR also you can. If you put 0, that will be the same, no change in the value. And all ones, earlier we did all zeros, all to become 0. Now here, if you want all to become 1s, then OR hash 111 number, binary number 1111. Or 1 will make everything 1. So that is all to that. Then you have further consideration of assembly language instructions. What are they? Register transfer notation. We did this in the processor fundamentals, but again we are coming into with a little bit of machine language or assembly language also. The LTD instruction is described by ACC is getting the value in the, this is the current instruction register, 15 to 0. That means the operand. 0 to 15, if you remember the diagram we saw, 0 to 15 is the operand, 16 bits. That will be loaded into the ACC. The instruction is in the CIR and only the 16-bit address needs to be examined to identify the location of the data in memory. The contents of that location are transferred into the accumulator. Again, I have copied this here, simple instruction format. This is the operand we are talking about, 16 bits. Task 6.02, yeah. Use register transfer notation to describe the execution of an LDI instruction. So you take anything from LDI something, and then you try to do it yourself. That is very important. Don't skip these tasks. And then computer arithmetic. The following worked example illustrates how the values stored in the status register can identify a specific overflow condition. The use of the following three flags is required. Carry flag, identified as C, which is set to 1 if there is a carry. The negative flag, N, to 1 if the result is negative. And the overflow, V, set to 1 if overflow is detected. That is how the computer knows. Otherwise, it just like humans, it can't think. They have to be guided, with like this, like spoon feeding. So here's an example, worked example. Using the status register during an arithmetic operation, consider the addition of two positive values where the sum of the two produces an answer that is too large to be correctly identified with the limited number of bits used to represent the values. For example, this figure 6.04, earlier one, shows that 6.0, figure 6.04, this is 6.05, that is this, I think, this 04, shows what happens if we use an 8-bit binary integer representation and attempt to add denary 66 to denary 68. So this is 64 plus 4. 1, 2, 4. 64 plus 4 is 68, and this is 66. 64 plus 2, 66. What happened? When you add up, you get a overflow, negative one. These two were, this became 1. Right? So because of that, there is a negative. So because of the flags, n equals 1. But there is no overflow. This overflow is 0. V is 0. If you look at the textbook, don't get misled. It says 1, but it has to be 0 because there is no overflow here. But if you add up and see, it will be 1. 1 plus 1 is 1, 0. 1 is carried, and here is 1. So there is no overflow. Only the negative value is there. Then consider the same 8-bit integer number. This time, negative. With the 1 in front, it's negative 66 and 68. So negative, it's different, no value. If you can't just calculate. So signed, if it is like 2's complement, same 8-bit binary integer representation, but this time we had two negative numbers, minus 66 and minus 68 in denary. So the result shown in figure 6.05, it's this, and there is an overflow. There is an overflow and a carry also, this coming. So not negative, it's 0 here. So n is 0 and V, this in the status register. Overflow is 1. There is overflow, there is carry bit. An attempted addition of denary minus 66 to denary minus 68. We get the answer plus 122. This impossibility can't, no, because it has to be minus, no? It has to be minus. This impossibility is detected by the combination of the negative flag not being set and both the overflow and the carry flag being set to 1. So these two, then it knows that it's this error. Now finally, tracing. Tracing algorithms, remember? So here is tracing an assembly language program. The main feature of this will be to check how the contents of the accumulator change as the program runs. The main feature of this will be to check how the contents of the accumulator change as the program runs. So tracing an assembly language program, for this example, the trace table needs a column for the accumulator, 2 for memory location, and 1 for the output. The tracing is based on an initial user input of 15, a second input of 27, and a final input of 31. So the program is shown here, and this is the trace table. So in, first one is, so when you say in, it's the 15 goes in. And accumulator gets 15. Then what is the next one? 101. Store 200. So in the memory location 200, this accumulator value is stored. Then 102, again in. So at 102, the number 27, 15, 27, and 31. So 27 comes. Afterwards, what happens? Add 200. What is there in 200? 15. Store, sorry, 103, store 201. So this 27 input will be stored here, memory location 201. Then again 104 in. The third input is 30, 31. So third input comes here, 31. Afterwards, add 200. 200 has 15. So 31 and 15, the accumulator becomes 46. Store 200. So in 246 will be stored. There. Add 201. 201 has 27. When you add these two, it becomes 73. Then increment ACC. So add 1, it becomes 74. And out. That means output this value, accumulator value, 74, and end. That is how you trace the program. It's very easy. Then worked example 6.03, tracing an assembly language program is another one. Similarly, some instructions for a part of a program are contained in memory location 100 upwards. Here's the address, 100 memory location. Some 4-bit binary data values are stored in locations 200 upwards. So here, some more, 200 upwards. For illustrative purposes, the instructions are shown in assembly language form. Here, at the start of a part of the program, the memory contents are as shown in figure 6.08, this one. Right, so then let's take one by one. Program counter 100, the instruction is LDD 200. And this is the accumulator column. 200 is here, 0001. Load to accumulator here. This is wrong. I didn't cut off, I just kept it. But this is in the textbook like this. It should be 0001 here. Then the next one is 101, the instruction number here. Increment ACC. So when you add 1 here, it becomes 10. Next is add 201. 201, where's 201 here? 11. When you add 11, what happens? It becomes 101. If you add 11 to this. If you take in denary, you can prove it. This is 2. 10 is 2 and this is 3. So 2 and 3 is 5 and this is 5. 101 is 5. Next, compare with 202. Compare the value of this accumulator here, 101, with contents of 202. Compare 202. It's equal, no? It's satisfied, no? Correct, true. Condition is satisfied. So then it's this 106. Jump to 106. So you bypass this. 105 is not, 105 is ignored. Or bypass this and go to 106. Increment ACC. That means that is 100. You have to give the values against the correct numbers. Okay. Or if you have to write the numbers, don't write those numbers which are not used. So when you increment this, 101 will become 110. That is in 6. Earlier it was 5, now it became 6. Then 107, store 203. So this will be stored in 203, which is here. Memory location 203, 0110. Stored there, and that's it. That's all. These are not necessary, these are unnecessary. Program ends here. Right? Then you have a task to carry out. Without looking at the explanation provided, trace the assembly language program shown in table 6.01. Earlier, use a value of 3 for max, 7, 8, and 9 as input values. So if you go to 6.01 table and use these values, 3 for max, and these are the input values, you should get the answer. You might not get the first time, don't worry. You just finished assembly, you just learned assembly language. So doesn't matter if you don't get it first time, but keep doing and you will succeed. So I hope you enjoyed this lesson and you learned something new. Try to do all the tasks and see how you improve in assembly language.